a beam like from a laser pointer, all of those rays which are entering parallel will converge to a single spot, and that's called the focal point. And that focal point resides on a plane called the focal plane that is a distance f, or one focal length away from the lens. Now, this is the proper way to think about light passing through a lens, but for people who want to prototype optical systems or get a quick estimate for how a system is working, oftentimes we use simpler equations. And a simple equation is shown here at the bottom. That's the lens maker's equation. And that lens maker's equation has two important simplifications. Number one, it assumes that the distance between the two surfaces of the lens are very small, so small as to be negligible. So we don't actually need to follow the light as it moves between one surface or another. The second important simplification it makes is that the surfaces can all be described by spheres. That is, they can all be described by a single number or radius of curvature. So once you know the radius of curvature of the two surfaces of your lens, and you know the index of the lens, that's the n in the equation, you can calculate how far away parallel rays entering this lens will converge. And that's the focal length. This is a very powerful equation because it gives us a very simple way of determining or designing what a lens should do and putting together simple systems. As we'll talk about in a moment, there are a number of caveats for this simple equation, things that aren't captured. But for purposes of designing systems and understanding how images are formed, this simple set of equations are very useful. Now, lenses come in many different shapes and sizes. The one I showed you just before was called a plano-convex lens. And the plano is because of one surface being a flat surface, or a radius of curvature that's infinite, and the second surface having a concave curvature, a plano-convex rather, convex curvature. And if you imagine two spheres that intersect, those two spheres intersecting can intersect in various ways, and each of those intersections will give you a different kind of lens. So here are the range of different the lens shapes that can be generated simply by intersecting two spheres. And if you have the correct sign notation for your radius of curvature, you can simply calculate where should the lens focus. And one interesting thing we'll get to at the very end is that the focal length doesn't always have to be a positive number. It can sometimes be a negative number. And when you have a negative focal length or a negative lens, the place where your image shows up is different, and the kind of image you get is different as well. But let's go back to the simple case of a thin lens focusing a bundle of rays down to a point. So the way I've drawn this here is very much a point. It seems to be infinitely small. But it's worth remembering that waves are not infinitely small. They have dimensions to them. They have wavelengths. And if you were to zoom in on that focal point, what does it really look like? Does it really look like a point? And the answer is no. This has been well known for a number of years. If you solve the full vector diffraction theories, then you get a distribution intensity that looks like this. Looks rather complicated. But there's a very important line that's drawn right here in the middle. And if you look at the intensity profile along that line, that's the so-called airy disk, which defines the point-spread function of your system. Now, this is a topic that will be covered in much greater depth in a different lecture. But this is simply a reminder that our simplifications are useful for understanding how systems are set up, but the details of resolution and of image quality often come down to diffraction level effects, such as those shown here. A couple other things that can affect, most often negatively, your imaging capabilities are aberrations. And there are two main flavors of aberrations. There are chromatic aberrations and monochromatic aberrations. The chromatic aberrations are because that n, that index of refraction that defines our material properties, that n actually happens to be a function of wavelength. There's not a single index for a material. The index of the material depends on what wavelength you're passing through it. So the index can be higher or lower for two different wavelengths, and therefore they will focus to different points. And correcting this has been a major challenge and one of the major advances in light microscopy over the last several decades. So the second kind of aberration is monochromatic aberrations. And monochromatic aberrations are those that occur even if you only have one wavelength passing through the material. And an example of one of the 5 major monochromatic aberrations is shown here. This is spherical aberration. And this comes from the fact that even though spherical surfaces are easiest to make, the sphere is not the perfect focusing shape. In fact, you need different shapes, aspheric shapes, in order to perfectly focus a given wavelength to a spot. But for large focal lengths, spheres tend to do a very good job, and spherical aberration is not as bad. And so again, the concept of thin lenses, where we only care about the index and the radius of curvature, those concepts are still useful in thinking about how imaging systems work. Okay, so let's build up our skills so that we can actually identify where the image of an object will show up on one side of the lens. So we're going to learn 3 tools of the trade, and those are ways of identifying where rays should go, where these representations of rays should go from a given point on an object. So if you think about an object as being something that is scattering light or emitting light, we have the option of picking a number of different rays coming from that and asking where do those go. So what we're going to do is we're going to be smart about picking rays that do things we know. And the first is that any ray that comes in parallel to the optical axis. The optical axis is this line all the way along the center of the imaging system. That optical axis, if the ray comes in parallel to it, the ray should converge through a positive lens through the focal point. Or if the ray comes in at an angle, it will still converge through the focal plane, but offset from the optical axis. So that's one very helpful rule. Parallel rays coming in go through the focus. The second helpful rule is just the opposite of that. If you have light coming from a focus, it will leave this lens as parallel rays. So you can imagine that those are the case because you could run these two diagrams, if you flip them around, they're the same. So there's one last rule of thumb for ray tracing, and that is rays that pass through the center of the lens are not refractive. So in reality, they are refracted a little bit, but the refraction is opposite. So you bend it one way, and then you bend it back the other way, so it comes out looking as if it hasn't been refracted at all. So those three things: rays coming in parallel pass through a focus, rays coming from the focus come out parallel, and any ray that passes through the middle of the lens isn't bent at all. So we can now use that to figure out where should an image show up if we have a lens in front of this object. So we'll start by tracing a few rays. So these rays are all coming from the tip of the object. So let's take this, the middle ray. So there's the middle ray is passing all the way through the center of the lens. And based on that rule number 3, we shouldn't bend it at all. That ray should pass all the way through and continue going. Now if you look at the bottom ray, that bottom ray is coming from the tip of our object. But we've chosen it so that it passes through the focal point of our lens, the front focal point of the lens. And what that means is that when it hits the lens, we know it must be coming out parallel to the optical axis. The optical axis is, again, this dotted line here. So where those two rays converge, that is where the tip of our image must be. The rays that came from that tip, the lens is converging them back to that tip, and that's what allows us to do the imaging. And that third ray is one that doesn't follow either of our rules, but we know that any light coming from that tip must end up at its conjugate point on this other tip. So these two planes, the object plane and the image plane, are known as conjugate planes, and the points within them, that from which light comes and to which light goes, are conjugate points. Now we can take other points on that same object and make the same set of arguments. That rays passing through the middle of the lens don't bend, rays that pass through the focus come out parallel, and we can identify the other parts, the other end of this object, as well as each point in between. Now this, we've used drawing essentially to figure out where things ought to go. But this drawing is a shortcut for some relatively simple math, which can also be used to calculate where an object and image are. So there are two equations that are worth remembering. One is the thin lens equation, which relates the distances from the object to the lens, and that's denoted SO, and the distance from the lens to the image, that's denoted SI. And those two quantities are related to S, the focal length, by this thin lens equation.